See what's next. Ah, okay.
Well, like the first couple times it kind of was that way. At this point, that's the thing. There's talking. There's one or two shades.
It shows you your little chart.
Well, I might pass this test yet.
Oh, is the Cisco test? No. This test.
My test.
My test. Yeah, okay.
You see something over there. Yeah, I mean, I know what I'm doing. Here's mine. I'm keeping my track.
Okay.
Yeah, I'm keeping my track.
I was going to say, ship the one that's the most valuable to you, I thought would be the...
No.
Okay.
My track's worth way more than...
okay. I just meant as far as utility, that's all.
Yeah, it's still my truck, because I can still put them all in that day.
Okay. Well, I was just thinking,
But, yeah, no,
why,
I have the time to really
if you're looking for like, if it's a 5-seater or 7-seater or something like that, if you're looking for, it might be hard to find that, but I just don't know what the market looks like as far as, second-hand vehicles, used vehicles, level lock type stuff, whatever, something that's reasonably priced.
That's what I was saying.
Things like it, I would assume are more expensive. So maybe you want to think about, if I go to buy a second vehicle, why, even if it's a used vehicle, what's going to be more expensive on the floor? Is it going to be a truck? Or is it going to be, a minivan of some nature? And then that is not research,
Yeah.
I don't know what people prefer there. My assumption is they're fights.
Yeah.
Maybe it's a wash. Everything works across the board. Maybe there's some pressure on which one is going to be more expensive. Once you get there, that's where you keep shit. The other one's going to sell. Based on that. Just something to think about.
And you don't want to just fire out because
used cars now get more expensive in some instances than new cars.
Yeah, you guys take
That's huge. That may not necessarily be.
you take your whole ranges on even day. Yeah,
You've got to do
Try to sell it.
and that's still a way that you can get used vehicles
I got a question about TSEC.
at a reasonable price.
That's not.
Which is better off than going and buying a new vehicle using all that
Why are you guys not doing this? Because you could.
So generally, I don't. The businesses maybe able to see how that works and raise the prices accordingly. So individual sellers were just going to like, this would work. I like keep it on this is plus or minus. They want to get rid of it because they already got a car.
It's so simple. It's so cool.
Before I went through so that may be still real way. Still easy to be your post.
First time you ever saw them.
And
they were small.
That's why.
Yeah, so.
I was kidding. I need something. I heard not six.
I don't know. I bought it.
I just don't know my primary school education.
I'm going to do it.
I remember doing this.
No, I'm not. I'm getting pretty much on.
And I look at the opportunity cost, like what I would do is, if I bought the used version and taken that extra and done something else, or maybe even bought two bits of vehicle, I could have bought 2 cars for the price I paid for the 1 car. Instead of me buying 1 car, I bought 2 pieces.
I'm messing up.
If you look at that, or I could have bought the 1 vehicle price of used car.
I know what it is.
Money, that's what I'm saying. years ago, and that was more than 20 hours contact with time. So thinking about stuff like that, and you're like, okay, so how can I do this the best way possible? You gotta ask yourself, in 5 years, are you going to think this is a smart purchase? Yeah, we should say this is the best we can do. I thought it was supposed to be today. Oh, no. I thought it was the 12th. No. Why would that be a good thing?
I almost feel like that.
Yeah, you know, that was kind of
I'm certainly not going to buy it. When I did,
I have to wake up 30 minutes earlier.
I was employed, the only thing I ever used was Excel. For number theory, basically, it all boils down to some sort of simple algorithm.
Well, we're going to do it over and under.
Like the color chart and everything. It's all basically all
Could one of us write it out?
I just hope that we
I guess it's
hopefully with that when you get released, so that'll be 61 hours. I'm just going to check my email at the house 45 minutes. And then we'll start class, and then we'll try and take Steve's chair. That's what I hope. Most people house. And then I hope we take a break for like an hour. For like, it was about an hour. And then we come back to another class, and then we take like 15 minute break, and then come back for 2 minutes. That's fine. That'd be awesome. I'm going to look at this. That would be the perfect day in Army. Only that could ever happen.
When did you prepare for the test?
Get with the test.
I believe Major General.
Last night, really nice one that he never really used because he's all
like, that Dr. Because it doesn't do it. He said, I'll sell it. It does everything.
Right, that's where the class on right. What I'm trying to do, like where you learn like
how different pieces of the spectrum are cut for you by like which agency to go to. Where it starts at the FCC and how it's carried down to the part where you get or like you get one emergency frequency that's shared by everyone on impulse. And so that's what the class was supposed to be. What the class actually was. That's like how it's well, it was right.
When you start talking about
satellite theory, what was the numbers so big that like you're multiplying, you're doubling something. Doesn't matter. Just ignore that. It was a black guy, but I mean, that's what it gets to be like. Trying to tell us like this level it's double or half. It's not make any physical difference to you.
You know, and then you're not anymore of that. 4 or 5 months, whatever it is.
One of the books we got.
I was in a situation.
One of the
I look at
we totally ranked higher.
one of the like radio.
I went to
All right. I'm running a little behind.
But all my time, guess I'm going to do it fast.
Okay, we're starting.
Okay. All right. So I'll start again. So I'm running just a little bit behind, so I'm going to breeze over the LCM because, well, all right. You take the prime factors, you take the two prime factorizations, you compare the exponents, and now you take the maximum of the two exponents. So look at the primes in either list, take the maximum of the exponents, multiply those together, that gives you the LCM, and I'm just going to skip the reasons for it, so I mean that's not important. But here the LCM of the two numbers, our two favorite numbers here, are 932, 400, so you take 2, 3, 5, 7, and 37, take whichever exponent is greater for each, and then take that to the exponent. That gives you the LCM. That just goes into the reasons. But we also have this rule, which I gave on the board already, is that to get the LCM, you can just take the product and divide by the GCD. That always gives you the LCM. So computing the LCM is no harder than just computing the GCD. So you really only need to know one algorithm to get the GCD, and that gives you the LCM pretty much for free. All right. And so we're not going to deal with any of this. I want to get on. Now, here is computing the Euler totient function from a prime factorization. So let n be a positive integer. And here is its prime factorization. So here, the q's are distinct primes. So no two q's are equal, because if they were equal, we would have just combined them and take the sum of the exponents. And these exponents here are some positive numbers. Okay. Then here you can write down, get a formula for phi of n as follows. It's a product. You take each prime exponent, each prime exponential. What you do is you take q1 to a1 minus 1. You subtract 1 from the exponent. And then you multiply that by the prime itself, minus 1. So, and do that for every prime factor. I can't walk over there. I'll show you my hand, but I can't. So here it is for q1 to the a1. You subtract 1 from the exponent, and still take q1 to the a1 minus 1, and then multiply that by the prime itself, minus 1. And do the same thing for q2, q3, all the way up through all the prime factors. Okay, and there's another way of writing it. It's n times this product, but you can ignore it. It's really this middle piece which gives it to you. Yes?
Why is that important? I guess. What's the so what for it?
The so what for computing, for knowing the totient function, yes. That's still coming.
Okay.
That's coming, yeah. I promise. I promise it's coming.
Calm down. It's going to be a surprise.
So let's compute phi of 5328. Phi of 5328 is 2 to the 4th times 3 squared times 37. So here's the prime factorization. So what's phi? Well, you're going to take 2 to the 3rd, which is 8, times 2 minus 1, which is 1. Then 3 to the 1st, which is 3, times 3 minus 1 is 2. And then 37 to the 0, which disappears. But you do still multiply by 37 minus 1. So you multiply that by 36. So here it all is. And you get that, and that's equal to 1728. So there are exactly 1728 numbers less than 5328, which are co-prime with it. All right, here is the topic I really want to get to, because we're going to spend most of the rest of our time with this, modular arithmetic. In this case, let's go back to the division algorithm for a second. So what does the division algorithm do? You have these two numbers, and you divide one by the other, and you get this quotient, and you get a remainder. The quotient actually is not as important as the remainder. And in modular arithmetic, we're only going to care about the remainder. We're not going to care about the quotient at all. So the modular arithmetic is all about the remainders when you do a division. So let n be a positive integer. We say that two integers a and b are congruent modulo n, written like this, or like this. You can write it in either way. I prefer the space. It's a little more compact. If they have the same remainder when you divide each by n. So you divide a by n, you divide b by n, take the remainders. If the remainders are equal, then we say that they're congruent. Equivalently, n is a divisor of n divides a minus b, the difference. So this is an equivalence relation. So everything is congruent to itself. Bless you. And it's symmetric. And if A is congruent to B and B is congruent to C, then A is congruent to C. So congruent modulo n chops up the integers into n many different classes called congruence classes, one for each possible remainder you can get. So what are the possible remainders when you divide by n?
N minus 1. Up to n.
Yeah, so 0 up through n minus 1. So there are exactly n many of them, n possibilities. So those are the n possible remainders. So now we group the integers together into classes depending on what the remainder is, what the common remainder is. So all the numbers in the same class are equivalent, are congruent. Okay. So, and we write this as so the congruence class containing A is written like this, A bracket with an N. So this is a set of all B's which are congruent to A. And so B is in this class if A and B are congruent, mod N. So we're fixing N here. N is just fixed throughout. N is sometimes called the modulus. So here's some properties. It's reflexive, symmetric, goes either way, that's pretty easy, and it's transitive. If these two have the same remainder and these two have the same remainder, then that's going to have the same. Those two are going to have the same remainder. So in particular, A and B are congruent if their congruence classes are the same. So if their congruence classes are different, then they're not congruent. Okay. If one is in the other. All right, some examples. So let's let 2 be the modulus up in this. So if 2 is the modulus, 7 is congruent to 3. Right? Because when you divide each by 2, the remainder is 1 in each case. Okay? Or equivalently, 7 minus 3 is 4, which is even. So the 2 divides 4. So 7 and 3 is also congruent to 1. Because they both have remainder 1, and their difference is even. Okay? So these are all the same congruence class, and now the integers are grouped up into 2 congruence classes, modulo 2, and these have names, the even numbers and the odd numbers. So the even numbers form one congruence class, and the odd numbers form the other one. So the even ones have remainder 0 when you divide by 2, and the odd ones have remainder 1. Those are the only 2 possible remainders. Let's take modulo 4. So 4 is now the modulus. So 7 is congruent to -1 mod 4. Because they both have the same remainder, what's the remainder? When you divide by 4, it's 3. So that's true, certainly true for 7. What about -1? So remember what you have to do for -1. You have to go hop back to -4 and then come back 3. So the remainder is 3 in that case. And if you take 7 minus a -1, you get 8, which is a multiple of 4. Likewise, 3 minus a -1 is 4. So that's a multiple of 4. So there are 4 congruence classes mod 4. How about mod 5? Mod 5, 7 is congruent to 2, because they both have remainder 2. Or, equivalently, 5 divides the difference of the 2. So 7 minus 2 is 5, divisible by 5.
Spinner.
Yeah.
kind of getting a little lost, but I think I'm picking it up. So pretty much, we'll have 7, and then we have congruence. You would tell us 5 or whatnot, and then we're just finding the remainder, correct?
Yeah, in this case, 2 is the remainder, but there are lots of 7 is going to be congruent to so infinitely many other numbers.
Yes.
Yeah.
But you would kind of say, hey, this is 7 uncongruent 5, and then we kind of find the remainder. Is that how this goes?
Yeah, it could, but I mean, this is also congruent to. It's always congruent to it. It's always congruent to it. It is always congruent to its remainder.
Okay.
That's always true. Good. So if you take a remainder and you try to divide it by the modulus, which is bigger than the remainder, quotient is going to be 0, and each remainder is its own remainder. So it's congruent. So every number is congruent to its remainder. Good. So the remainder of 7 when you divide by 2 is when you divide by 5. I'm going too fast. The remainder of 7 when you divide by 5 is 2. The remainder of 2 when you divide by 5 is also 2. It's itself. So 7 is congruent. And that's true for any modules. All right. Good point. If you look at an equivalence, if you look at a congruence class, say mod 5, the numbers in the class are evenly spaced on the number line, and the 2 adjacent numbers are always distance 5 from each other. So, for example, these are all the same equivalence class. They're the same congruence class. They're all the ones that have remainder 2 when you divide by 5, and that includes -3, 2, 7, 12. These numbers just skip by 5. That's true always. So if you have a modulus n, and you look at any congruence class modulo n, the numbers in that congruence class are evenly spaced, mod n. Here's another way to look at it. Let's say mod 5. Those are the 5 possible remainders, right? Mod 5, 0 through 4. Well, I'm just going to write down all the integers, but I'm going to restrict myself to these 5 columns. So if I continue on with 5, I'm going to wrap around to the next row. And then 10, 11, 12, 13, 14, 15, etc., that way. And going backwards, I can also go backwards. So this will be -1, -2, -3, -4, -5, -6. And so on that way. So if I group all the numbers, all the integers like this into these 5 columns, the columns are the congruence classes. So these are all the numbers that are congruent to 0, mod 5. These have remainder 0. So these are all the multiples of 5. All of these numbers are multiples of 5 plus 1. So they're all congruent to each other, but they all have remainder 1 when you divide by 5. Likewise, these have remainder 2, remainder 3, and remainder 4, which is easy to check. Okay. And if you look at sort of, I'll call that the primary row, the row that contains 0, this gives you the actual remainders themselves. See that? Okay, so that's another way of looking at it. So those are the congruence classes. So now here's what we're going to do. Okay, so I guess more. So we're going to define, so for n as a positive integer, I'm going to define z sub n to just be the set of all possible remainders when you divide by n. So we call these the remainders modulo n. They're also sometimes called the residues modulo n. Remainder and residue being the same thing. So for example, z sub 2 is just 0 to 1, z sub 4 is 0 to 3. So it's just the integers from 0 up through n minus 1. That's all it is. Okay. So Z sub n represents all the congruence classes, right? Because every column is represented. So this is Z sub 5. That's Z sub 5 right there. All the congruence classes are represented, and in fact, every congruence class has a unique representative, a unique member in Z sub n. Okay? Namely, the remainder. So, given A and N, by the division algorithm, there's a unique Q and R such that this is true. So, A is equal to Qn plus R, and R is in this range. Well, if I take A minus R, I get a multiple of N, Q times N. So this is why it's equivalent to N dividing the difference. So this just says that N divides the difference of A and R. So A is always congruent to its remainder, modulo N, which is what I answered to Captain Langley before. All right. So the unique element of Z sub n that represents a number A, we'll denote this by A with a subscript n. So A sub n, this is just A mod n, which is the remainder R. So remainder when dividing A by n. So we're going to use that notation. So for example, 7 mod 2 is 1, that's the remainder. That's equal to 3 mod 2. 7 mod 4 is 3, which is also equal to negative 1 mod 4. And 7 mod 5 is 2. These are all just the remainders. So we don't care about the quotients anymore. We just care about the remainder. Now, here's the fun part. This is what makes this interesting, is that we can redefine the arithmetic operations, but now confined to Z sub n. So we call this modular arithmetic. So if I add two numbers, if I add any two numbers here, let's suppose I add negative 4 and 13. What do I get? I get 9. Okay, so negative 4 and 13 is 9. So notice, negative 4 is in this column, and 13 is in that column. I add them together, I get something in this column. Let's try two other numbers in the same column. How about 6 plus 3? Or 6 plus 8? 14? That's also in that column. In fact, this is actually true anywhere. If I take any two numbers from two columns, or possibly the same column, and add them, no matter which numbers I choose, the column of the sum will always be the same. Okay. And here's how you get that column. You just take the numbers and you add them, as usual, and then you divide by the modulus n. That tells you what column you're in. And that gives you a unique number in Z sub n. So that's called modular arithmetic. If I take any two numbers A and B, I'm going to add them mod n. That's a plus with an n subscript. I just add them normally, and then I take the remainder, modulo n. Okay. Likewise, we can do the same thing with multiplication. A times n times b modulo n is the usual product, AB, but then I take the remainder divided by n. So notice when I do this, I'll always get the result. The result will always be in Z sub n. Right? Because it's a remainder mod n. So it's going to be in Z sub n. And furthermore, the result only depends. It only depends on what equivalence classes A and B are in. Only what congruence classes they're in. So there's another way of saying that. Well, I'll get there. But I've got this operation that always gives you something in Z sub n. And the operation has some of the similar properties that you expect. So it's associative, doesn't matter how you group it. Both operations are associative. I've got an identity element. If I add 0 to a number, I get A. These are for all A, B, and C now in Z sub n. If I multiply it by 1, I get back A. It's commutative. I got a distributive law. Multiplication distributes over addition. And 0 times anything is still 0. So all of this is true, but maybe we should see an example. So let's take Z6. These operations now are operations, you can think of them just confined to Z6. Right? You can define them for all the numbers. But since the result only depends on the remainders, you might as well just confine yourself to Z6. Okay. So if I add 2 plus 4 mod 6, well, 2 plus 4 in real life is 6. And what's that remainder then? Is 0. Okay, so this is going to be 0. And then if I add that 5 to that, I get 0 plus 5, which is 5 in real life. But then when I divide by 6, I still get 5, because 5 is less than 6. So that's 5. So 2 plus 4 plus 5 is equal to 5. Modulo 6. 2 plus 4 plus 5, if I group it this way, 4 plus 5 is 9. Modulo 6, what's that? 3. And if I add that 2 plus 3 in real life, I get 5 again, which is its own remainder, mod 6, so I get 5. So this illustrates the associative law. Likewise, for multiplication, 2 times 4 times 5. Well, 2 times 4 is 8. Mod 6, what's that going to be? 2. Times 5 again, in real life, that's 10. Modulo 8, that's 2. I'm sorry, modulo 6, that's 4. So I get 4. Or I could take 4 times 5. I get 20. Mod 6, that's 6, 12, 18, plus 2. It's 20. Times another 2, that's 4. And divide by 6, you still get 4. All right, and here's the distributive law. I'm going to skip over that. Let's do something. Let's do this mod 5. Let's do an addition table. Just for fun. So think of this as an operation just on Z5. Takes 2 numbers in Z5 and returns another number in Z5. Well, 0 plus anything is just that thing. I'm sorry. Yeah, and that's right. But 0, and so I can do this in both directions. Now filling up the rest of the table, 1 plus 1 is what? 2. And when you divide by 5, you still get 2. 1 plus 2, 3. 1 plus 3, 4. 1 plus 4. It's 5 in real life. But now when you divide by 5 and take the remainder, it's 0. So basically, when you count up and you're doing everything in Z5, once you get to 5, you cycle back to 0. That's really what's going on. Let's do it. So 2 plus 1 is 3, 4, 0, and then 2 plus 4 is 6. All right, see that? So as you're adding, if you keep adding 1, as soon as you get to 5, you just cycle around to 0 again. And then you keep adding, and then you go from there. Okay. 3 plus 1 is 4. 0, 1, 2. 4 plus 1 is 0. 1, 2, 3. Let's try that. 4 plus 4 is 8. That has a remainder of 3 when you divide by 5. Okay? So, when you add on the number line, if you add two numbers, well, you can go that direction, and that's A. And then when you add B to it, you start at A, and then you skip B, and that gives you A plus B. Well, now we're doing the same thing, except think of the number line as sort of wrap the number line around itself into a circle. So that's 0, that's 1, 2, 3, 4, and then 5 is identified with 0. And now you're adding along the circle. So now you're moving along the circle rather than moving along the number line. And if you just wrap more than once around the circle, you just start over. You repeat back at 0. So 4 plus 1 is 0, and you keep adding 1. So think of this as it's sometimes called clock addition. So that would be addition mod 12. So when you take, you take 11 o'clock and add 3 hours to that, you get 2 o'clock rather than 14 o'clock for a 12-hour clock in the military.
Yeah, put that in there.
All right, and we can do a multiplication table, can't we? So I'm going to get zeros all the way along here. Let's try ones. I get 0, 1, 2, 3, 4. Oops. 2, 3, 4. 2, 3, 4. Now I'm skipping by 2's for the next row. So 0, 2, 4. What's next? It would be 6 in real life. But what is that on 5? 1. And then the next one would be 3. And then 0, 3. Now I'm skipping by 3. So the next one would be 6, which is 1. And then the next one would be skipping by 3's, 4. That's still. And then skipping by 3's again, it would be 7 in real life, which is 2. Let's try that. So this is 3 times 4 is 12. Remainder is 2. 3 times 3 is 9. That has a remainder of 4. So 4, I'll fill that in. 4 is going to be 0, 4. What's the next one? 3, 2. Yeah.
4. So 4 times 3, 12.
4 times 3 is 12.
So are we going, is it 5 times 2 is 10, so then we got 2 remaining?
Exactly. So it's the remainder.
Okay.
Yeah. Quotient.
So every 5 week, I guess so like...
No, every 5, you just go back to 0, basically.
Okay, so like if it would have been, like let's say it would have, exactly like 4 times 4 is 16, that would go all the way up to 15, go back 1.
Well, you continue on 1.
Continue on.
Yeah, right, so the remainder's 1. Yeah, think about counting to 12 on this circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Every 5, you just go back to 0, so the net amount you move is just the remainder after you've gone through all your multiples of 5. All right. So let's evaluate this. Modulo 13. This is not meant to be difficult, and you can do this easily without a calculator. Why can you do it easily without a calculator? And the reason is because you can take this product, and if you only care what its remainder is, mod 13, you only care what congruence class it's in. you can take any number here and freely replace it with something congruent to it, mod 13. So you can make these numbers much smaller. You can make them much closer to 0 that way. And so you're multiplying much smaller numbers together. Yes. You can replace 29 with 3, exactly, because 29 is congruent to 3, mod 13. When you do any arithmetic and the final answer is going to be just the remainder of the result, you can freely replace anything in that expression with something congruent to it, and that will not change the answer. So, 29 you can replace by 3 because 29 is congruent to 3, mod 13, right? So 13 times 2 is 26. Then to get 29, you add 3. That's the remainder of 3. 42 is also congruent to 3, so replace that with 3. Negative 61.
Why do you have a negative? That's what I don't use the negative there, because I thought remainders had to be positive. Is that not true for modulus?
So yeah, the remainders do have to be positive or 0, but I don't have to have a remainder here. I don't have to choose a remainder. I can choose if the remainder is going to be big, if it's going to be like 12, I don't have to pick 12. I can pick minus 1 instead.
Okay.
Which is not an official remainder, but it is congruent to 12.
Okay.
All right. So minus 61, well, minus 5 times 13 is minus 65. Come back 4. So the remainder is 4. And now 116, well, 13 goes into 117 evenly. And then now you come back minus 1. So 116 is congruent to negative 1. It's also congruent to 12. That would be the official remainder. But 12 is but negative 1 is a lot closer to 0 than 12 is.
So basically, if it's over half of the modulus, then you can just make it a negative number to make it smaller?
Yeah, sure. Yeah, if the remainder is more than half the modulus, if you take the negative, if you subtract the modulus, you'll get a number that's closer to 0 on the other side. It'll be negative. All right? So we do that systematically all the way through.
Would you be wrong if you left the larger one?
You would not be wrong if you left the larger one. It might be a little bit more work, but you will not be wrong. So 3, 81. There's also 3. Minus 5, just leave it as minus 5. That you can't really improve that. 85, 7, or negative 6, but it's pretty close. And 147 takes the remainder 4. Okay? So we've reduced these numbers to much smaller numbers. Now we can start multiplying. And now the point is, you can start multiplying, but when the number starts getting too big, just take its remainder, or reduce it modulo 13 to make it smaller. So you can do this at any time you want to. So let's say 3 times 3 times 4 is 36. So group these so that the products aren't too big to do in your head. So negative 1 times 3 times 3 times negative 5 gives you a plus 45. And then 7 times 4 is 28. Now I can do the same thing. I replace 36 with something congruent to it, mod 13. And minus 3 works because 39 is a multiple of 13. You come back 3, you get the 36. 45 gives you remainder 6, and 28 gives you remainder of 2. Multiply those two together, you get minus 36. And this is congruent to 3. Now, this has to be the correct answer because this is an official remainder. This is in the official range of remainders, modulo 13, from 0 to 12. So this is in the range, so it must be this value. So this value is equal to 3. Okay? Yes.
Did you get all of the number of terms in that multiplication
Yeah.
to be one of the official remainders? Could you not just add them up and divide by 13?
Well, you're not adding, in this case, you're multiplying.
Well, no, but I mean, if you got them all, like, instead of the -1, you had 12.
12,
Instead of
okay.
5,
You had 8. Yeah.
then you'd have nothing but the remainders. Could you just add them up and divide by 13?
Well, you're not adding them, you're multiplying.
Then you get the same. What does that mean?
No, you won't get the same answer. No. Well, you might be lucky and get the same answer, but not in general. You won't get the same answer.
Okay.
The thing is, you're multiplying these things. So, I mean, you could have a 12 here and you could have an 8 here, and you'll get the same answer in the end. It just might be a little harder for you if you don't have a calculator. So the answer here is 3. So here are the properties that we're using repeatedly. If two numbers are congruent, mod n, and you can add the same thing to them or multiply the same thing to them, and the result is congruent. So this tells you that in something like this, you can replace A by something congruent, and you get the same answer. You get something that's congruent, the result is congruent. Here, you can replace A by B. And because A and B are congruent, the products will also be congruent. So that's what we're doing here. We're replacing some factor by something congruent to it, and the product will be congruent. So we're staying within the same congruence class as we're doing all these calculations. And so in the end, all we care about is what the official representative of that class is, and that's the remainder. So that's in the range 0 through 12. Yes. All right. Let's do another example. 2 to the power of 30 mod 35. Oh, yeah.
Okay.
Now, recently made calculators can actually do this quite quickly, but we're going to see how it's done without a calculator. So the thing not to do is to take 2 to the power of 30 and just write it out as this big decimal, and then try to divide by 35 and find out the remainder. That's the hard way. The easy way is to break up 2 to the 30 into a product of things. So, for example, 30 is 5 times 6. So you can write 2 to the 30 as 2 to the 5th. All that to the power of 6. So what's 2 to the 5th? 32, which is, it's bigger, well, it's close to 35, but it's still, it's still 2 digits. So, we kind of still, our brains can still handle it. So this is 32 basically multiplied by itself 6 times. So now we use the principle that we can replace 32, each one of these 32, by something congruent to it mod 35, and it's congruent to -3. Yes?
Why did the 6 stay there? I don't.
Where, from here to there?
No, from the 2 to the 30 to 2 to the 5 with 6.
You're trying to get as close to 35.
Oh, okay. So why did we do it? Why did we do it this way? Well, you see why this is true, right?
2 to the 5th times to the 6 is
Okay. So it's
So
all
multiply
okay,
the
got it.
exponents. Okay. The reason why we did that in the first place is now this inner thing, we want to get something that reduces to something nice.
I was thinking for some reason the reason we did that was because the difference between 30 to the power up there and the modulus is 5. So
No, so the exponent here, 30, actually has nothing to do with the modulus.
okay.
Yeah, that's a false connection. All right, so 32 is congruent to 3. So replace each of these 6 factors by -3. We get -3 to the 6. -3 to an even power, the minuses are going to cancel, and we're left with +3 to the 6. Let's break that down into pieces that we can then reduce easily. So that's, say, 3 to the 4th times 3 to the 2nd, because 6 is 4 plus 2. 3 to the 4th is 81. It's still not too big for our brains to handle. 3 squared is 9. Now we can reduce 81 mod 35. And 35 times 2 is 70, plus an 11 to get 81, so the remainder is 11. So that's 11 times 9. So 81, we replace 81 by 11, and we get something congruent to it. So 11 times 9 is 91, and now when we take the remainder, mod 35 of 99, it's going to be 29. Because 70 plus 29 gives you 99. So that's the answer, 29. No calculator. All right, quick, reasonably quick. Questions? So that's 29. So the thing is, you can have a really huge number in here, but if you only care about its remainder, mod 35, you can break this down into really small pieces by reducing mod 35 and get quickly. Yes?
I get the 11 times 9 is 29.
Mm-hmm.
I don't understand how we get 29.
Because 99 is congruent to 29, mod 35. So again, I'm freely reducing. I'm replacing some number with some other number congruent to it. Why did I pick 29 here? Because now this is one of the remainders, one of the possible remainders when you divide by 35. So it must be equal to this. So the point is to get a number that really is one of the legal remainders.
I got you.
And then that has to be equal to that, because that's one of the legal remainders. It's a unique remainder and it's congruent to it. All right. We could have done this an alternate way. Instead of 3 to the 6, we could break that down as 3 cubed squared. And then 3 cubed is 27. And then replace each of these two 27s by minus 8. So 27 and minus 8 differ by 35. And so minus 8 squared is 64. And 64, when you take the remainder mod 35, you also get 24. You could have done it that way. So there's not necessarily one correct way of doing it. Okay, questions on this? Yeah.
My usual question is,
Yeah,
so what?
What is it doing?
Why?
Why?
You will receive cake at the end of this.
I'll tell you why. Okay, you can systematize this idea. In other words, there are fast algorithms to compute modular exponentiation. Do modular exponentiation. Modular exponentiation is like the workhorse of cryptography.
Okay.
I mean, that in a nutshell is why.
I'm good. I just understand we need to know this for the basis of cryptography.
Yeah.
I'm good with that.
Yeah. Okay.
Yeah.
So, let's do one more. I can't read that. 2 to the 34 mod 35. Can we help with this? Well, 2 to the 34 is 2 to the 30 times 2 to the 4. Now, we already did 2 to the 30 mod 35, so we can just replace this already with what we know it's congruent to. It's congruent to 29. So this is 29 times 2 to the 4, which is 16. 29 is congruent to minus 6, because these differ by 35. So we can replace 29 with minus 6. And 6 times 16, I guess that's 96, but I don't know my times tables that well. So what I'm going to do is I'm going to change that. It's the same thing as minus 24 times 4. What I do is I take a 4 out of the 16 and multiply it into the 6 to make the 6 a 24, and then I have 4 left over here. And now I reduce minus 24 is equivalent to positive 11 mod 25, so I reduce it that way. Now I can multiply those two. I know how to do that. That's 44, which is congruent to 9. And now this is an official remainder, so this must equal that. So that's equal to 9. All right. Do I have time for one more thing?